which we proved the QMA, the quantum co-clevin theorem, which showed that the local Hamiltonian problem, let's write it here, is QMA hard and QMA and in QMA. So local Hamiltonian problem. We'll use it. So I'm going to leave it on the board for some time. So we have the sum over HI. These are local terms, acting each one on K qubits, say, out of N qubits. And so this is H. And we're also given A and B such that B minus A is larger than 1 over polynomial. And we want to know if the ground energy of H is smaller than A, that's a yes instance, or larger than B. That's a local Hamiltonian problem, and the co-clevin theorem, the quantum co-clevin theorem, shows that this is QMA complete. Using this circuit to Hamiltonian reduction, circuit to Hamiltonian construction. So, okay, good. So, I wanted to start my talk, I wanted to sort of build my way up towards the quantum PCP conjecture and questions coming out of it. But before I do that, it will take some time to get there. So I want to start with, first of all, saying a little bit about what happened after this, this proof came out and people started to understand it. And so this question, first of all, the proof that I gave only gave local Hamiltonian, which is logarithmically local. Okay, so the way to actually move to a local Hamiltonian is not very interesting, but it is interesting. Essentially, the idea is that you have a clock, and instead of just writing the time as a number, you present it as a unitary, in some unitary representation, like a unitary representation like this, where here t ones and the rest are zeros, and you make sure by local constraints that the configuration is correct. And then to move from t to t plus 1, you just flip this bit, so it's also local. So that's basically the idea. So then, starting from this result, people started to ask what is the possible, what are the other Hamiltonians we can say things about, what other Hamiltonians are QMA hard, what classes of Hamiltonians, how much can we restrict the class of Hamiltonians so that it is still QMA hard. And all these proofs were based on basically better and more clever constructions of the clocks. And also on gadgets, which essentially take one Hamiltonian and simulate by another in very similar ways to how NP reductions work. Like you have some property which is local, and you simulate it by another property, by some other property that you want to simulate, and you apply this gadget. If you're familiar with this, that rings a bell, otherwise forget what I'm saying. Okay, so there are also quantum gadgets. Now, using these tools, there were several results that came out. First of all, as Zvika asked, the local Hamiltonian for two local Hamiltonians on qubits is QMA hard. QMA complete. And you can ask if, okay, so that's one thing, yes. Another thing that you can ask is what happens if you now put the particles in some restricted geometrical construction? Like say you put it on a two-dimensional array. Is it still QMA hard? So yes. And the surprising thing is that even if you put it on one array, it is still QMA hard. And this is very surprising if you know that a constraint satisfaction problem classically, if you put your variables on an array, a one-dimensional array, and your constraints only involve nearest neighbors, Do you know what's the complexity of this?
It's on bits or?
Yeah, it's dynamical programming. So it's simply.
I represent bits or?
I'm sorry?
This is of size 2 or size 1 or 2?
It's some constant, doesn't matter. But dynamical programming gives you UMP. And quantumly, you have QMA hardness. So where does this difference come from? It comes from the fact that basically the time in the clock, the superposition gives you an extra dimension. So in fact, we're working in 2 dimensions, even though we're working in physical 1 dimension. So that's one way to explain it. So 1D is still QMA hard. Okay, and not only that, if you require that the system is, yeah.
Just to clarify, 1D means that each of the local Hamiltonian only talks about particle j and j plus 1? Like, these are
Yes,
the only...
but not qubits. Higher dimensional particles, 8-dimensional particles, but yes. Yeah.
So what is the class of complexity?
P. This is a surprising separation. You can even achieve this in translation invariant system. So if everything here is the same, translation invariant systems, in this case, you can't really define QMA hardness because there's no input, because everything is the same. So you can't really put an input when you know the constraints. There's only an input of what is the interaction locally, but you have to repeat it. So basically the input is the size of the system, so you have to do to define it correctly, but then you can even get hardness with translation invariant systems, if you define it correctly. Okay, and then this sort of opened up, so basically you would like to sort of classify what kind of Hamiltonians are hard or not, and this would give you what kind of states, ground states of what Hamiltonians you would expect to be efficiently describable, or questions like that. This, by the way, came as a rather big surprise for physicists, because 1D systems, usually physics intuition is that it's easy, but if you allow yourself to be arbitrary, then it's not. Okay, so now you can ask what other questions are there? What kind of restrictions of QMA or local Hamiltonians are interesting to talk about? And one question was already mentioned by Thomas as a remark in my talk, the last talk I think, I don't know, last morning, the question of commuting local Hamiltonians. Commuting local Hamiltonians is the same as local Hamiltonians, but where all the terms mutually commute. Okay? Now, when all the terms mutually commute, you would think that the thing looks classical because everything is diagonalizable in the same basis, but it's not. And actually, I want to devote about 20 minutes to talk about this question, because this is what will lead us to the question to various questions about quantum PCP. So this is somewhere in QMA, contains anything, but we don't know where it is. That's a bigger question. So, okay. So why do you think this is interesting? So the thing is that even commuting local Hamiltonians, even though they're commuting, this is it's a disturbing question, because oftentimes people think about quantum mechanics as if the quantumness comes from the non-commutativity of things. This is a commuting problem, and still there is a lot of, seems to be, to enable quantumness in it. I'm saying it deliberately very vaguely so that actually it makes sense. Okay, so the thing is that with these commuting local Hamiltonians, we can have ground states which are highly entangled, even though they're commuting. And actually we saw such an example. We saw examples of these. Do you know? Hmm?
The GHS.
No, the GHS state is not the ground state of a local commuting Hamiltonian.
But it's stabilized.
I'm sorry?
But it's stabilized.
Yeah, but it's not very highly non-local, so yeah, it is an example of a ground state of some point, but if it's highly non-local, then sort of you wouldn't be surprised that there are non-local correlations. So we've seen it yesterday evening when I described stabilizer codes. So stabilizer codes can be actually viewed. I will repeat this in a moment. Stabilizer codes can actually be viewed as commuting local Hamiltonians. The codes are ground spaces of commuting local Hamiltonians because the stabilizers can be viewed as terms in a commuting local Hamiltonian. Stabilizers need to commute, right? So let me explain how this works. So stabilizer codes. This is a reminder. Remember, we have a Pauli group, Pn, which is I, X, Y, Z, tensor N. And the stabilizer is the group generated by K stabilizers, where each one here is something in the Pauli group. And you require that they commute. And remember that the Pauli elements either commute or anti-commute. Okay? And the stabilizer code is the one eigenvector, the code is the set of states which are the one eigenvectors of all stabilizers. Okay? And if these S's, say there are I, X, X, I, whatever, if these X's have weight which is constant, then I claim that this code is the ground space of a local commuting Hamiltonian. Why is that? Well, remember that the eigenvalues of these stabilizers are either plus or minus 1. So I'm going to just flip it so that the eigenvalue minus 1 becomes 1, and the eigenvalue 1 becomes 0. So let me just write it. So if I have I minus Si over 2 as my commuting local Hamiltonian terms, these terms commute as well, of course. Their eigenvalues were, well, 1 goes to 0, and minus 1 goes to 1. Right? So I get some projection. So now I have a set of, if these stabilizers were local, I have a set of local projectors that are commuting, and they have the same ground space. Their ground space is exactly the stabilizer code. Yeah? No? Question? Okay. So now let me say, I want to give an example that will be a running example. Will be very useful for us, the Torah code. Before that, I want to remind you of the procedure or how we think of correcting errors of the stabilizer code. And maybe also slightly be more careful with something I said yesterday, which was slightly not so careful. So remember that every Pauli either commutes or anti-commutes with every stabilizer. And we define the logical operators. So N in the Pauli group is a logical operator if for all S in the stabilizer, ES is equal to SE. It commutes. Okay, give me a logical operator that's obviously a logical operator.
I mean L?
Yeah, thanks. So give me an obvious set of logical operators. Identity, yes, but another set, like a larger set.
The stabilizer.
All elements in the stabilizer group commute with the stabilizer elements by definition, because the stabilizer group is commutative. So everything in the stabilizer is a logical operator, but it is an identity logical operator. So we should think of a logical operator as something, I showed it yesterday, that takes a word in the code and leaves it as a word in the code. Okay? But this kind of logical operator, where L is in the stabilizer, just leaves the word exactly as it is. It does identity. So these are not interesting logical operators, those that are in the stabilizer. So yesterday I was talking about the minimum weight of a logical operator. We should actually talk about the minimum weight of a logical operator which is not in the stabilizer. Okay, so let D be the minimum weight of L not in the stabilizer group. Now I'm claiming that you can correct what I wrote yesterday was correct. It was still correct, but this is much more powerful. Suppose now you have an error which is of weight at most d over 2, less than that. So if you have an error less than d over 2, I'm being sloppy here with the minus ones, but it's strictly less than d over 2, then I can correct it. And why is that? So if you remember, I defined the syndrome as for each element in the stabilizer, in the generators of the stabilizer, I check whether that stabilizer commutes with the error or anti-commutes. And in exactly those locations where it anti-commutes, I put a -1, and if it commutes, I put a 1. And that's my syndrome. It's a list of numbers, plus -1. Okay? So my syndrome for E is +1, -1, whatever, according to whether it commutes with each of the stabilizers. Now suppose I have two errors which have the same syndrome. What do we know about them? Two errors of this weight. So suppose I have E1 and E2 with the same syndrome. What's the syndrome of E1 times E2? That we already found yesterday. It's just, it's a product. So it's just, what's the vector here? If both of them have, if they have the same syndrome, what's the syndrome of the product of them? One everywhere. So it commutes with all the stabilizer elements. So E1 times E2 is a logical operator by definition. But because this weight is less than D, it must be, by definition of D, it must be a trivial logical operator. So it must be in the stabilizer. So this is in the stabilizer. If E1, E2 have same syndrome. Okay? So now the only way for me to correct an error is to look at the syndrome and somehow guess what the error was among all the errors that have the same syndrome. So what I'll do, I'll just pick one error with the same syndrome of distance less than d over 2. And I'll correct by just applying that error. So suppose E1 happened, I'm applying again E1 that corrects it. But now what happened if I guessed incorrectly? It was actually E2, and I guessed E1. Then actually the state that we have is this. Right? This is the actual error. It has the same syndrome as E1. So I applied E1, and I get this state. What's this state? It's exactly psi because this is in a stabilizer. Okay? So what I'm saying is that this is something that's highly non-classical. We can have different errors to correct the same state. So we flip different bits and we get back to the same state, and still we are okay. Yeah?
What's the definition of weight again?
Weight is the number of non-zero places in, so non-identity locations. So this is, for example, of weight 2. An error is a product of powers. It is the weight is the number of places where it's non-identity. Okay? So, good.
In the usual error correcting codes, what do these stabilizers correspond to, like those S?
I'm sorry?
Like how do we think of those S? How do we see those S in the usual error correcting codes? What do these correspond to? These stabilizers? S?
What do you mean by the usual error correcting code? Like the...
Classical.
Oh, then the S's will just be Z's. And then if you have here Z, 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 then basically that means that the parity, if you require that, say you have Z, 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 Z has plus or minus eigenvalues, that actually means that the parity of those bits on which you have a Z is even. So it's a parity check. Yes. Okay, so now I want to give a very beautiful example of a stabilizer code. And let's keep Tyler's Torah code. Okay, so the Torah code is defined as follows. You have a torus, and that torus has on top of it some grid. So we actually think of this as a grid. Say square root of n by square root of n grid. And on each edge, there is a qubit. And these edges are identified, and these edges and these edges are identified, so we have a torus. Okay? These are our qubits. What are the stabilizers? The stabilizers are this. For every vertex, we define a stabilizer acting non-trivially only on the edges going out of the vertex. And the way it is defined is Z, Z, Z in all these qubits. So for those in the back, it looks like this. Z, 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 and Z on the qubits. And for every, what's called plaquette, for every face, we have X, 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 X. And you can easily check, and you do that for every plaquette and for every face, and for every vertex. And so how many constraints do you have? There are n qubits. 2n, basically. You have a plaquette per qubit, and or per vertex, and you have a constraint per vector, per vertex as well.
Like 2n, I understand.
Did I mess up? Is this foreign?
So is every qubit belongs to two vertices and to two plaquettes?
Sorry, it's 4, right? It's 4. It's 4. Okay. So 4n constraints. Let's denote it by m. Okay. So now let's see which errors do you correct, and what happens in this, what's the distance, and what kind of errors you cannot correct, what are the logical errors. So
Dorit, so somehow surprisingly, if you notice it now we have more constraints in variables?
I'm not sure I did the count. It's maybe by 2, but not by much. So maybe I got confused with a constant, but should we delay this? It's not. It shouldn't worry you. It's
No, I mean, just classically it doesn't make sense, but then we said somehow quantumly it doesn't make sense, the more constraints.
I'm just not sure, but I did the constant and I don't want to spend time on it. Maybe someone in the back can compute this.
But if this fall was 2, it was going to be twice as many constraints as variables, right?
I think that the constraint is only on the vertex, so it should be 2n. You're imposing a constraint on each vertex.
Just the
I
constraint
really
doesn't
don't want to
determine
spend
the
time.
stage.
Okay, let's not spend time. The question is not it's not a problem. I'll show you in a moment, and let's just call it C times N. And if someone figures out the right answer, just tell me. Okay, so Thomas, did you?
I was just saying that I think it should be factor 2, and being off by factor 2 is normal. You have twice as many constraints as variables, slightly less than twice as many, and that's fine because there's the x and the z basis. So if you take the linear code, it's fine to have twice as many constraints. Some
Okay.
of them are x and some of them are z.
Let's postpone this question. So this is not the. Okay. So I want to ask what kind of errors can I correct? How can I correct errors? So suppose there was an error that looked like this. X here, X here, X here, and X here. Is this an error at all? Suppose someone came to the state and actually flipped those 4 qubits. It's nothing because it's in a stabilizer. What about looking at a loop here, like this, with x's here on every edge? Is this an error? Yeah, it's also stabilizer because it's actually a product of the stabilizer here, 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 and here, just that the x's here cancel out because we have 2 of them. Okay. Good. So now, suppose I have an error which doesn't close a loop. It looks like this. Is this an error? The answer is yes. It is an error, and you should be able to see it because it doesn't commute with the stabilizers, and as we said at least yesterday, if your error doesn't commute with one of the stabilizers, then it is an error. It takes you out of the code. So this is an error. Which stabilizers don't commute with it? Or how many stabilizers don't commute?
Maybe one of the z's, the ends.
Yeah, right, so exactly. If I have a ZZ here, then it doesn't commute because there's only Z and X here. But if I have Z, if I look at somewhere in the middle, then a vertex, a ZZZ, and somewhere in the middle here has 2 intersections, so we have XX and ZZ, so they commute. This is actually also the reason why the whole stabilizers commute, because vertex and the plaquette either intersect in 2 locations or in 0 locations, so they commute. So, okay, so this is an error, but it only sort of shouts there's only 2 constraints that are validated. This and this in the projection. Okay. And the rest are not validated. So the syndrome only gives me an indication that this guy and this guy is validated, are validated, and so I cannot know that this was the error. So my way to correct it would be, I don't know, to connect it somehow. But the nice thing is that even if I corrected it in a wrong way, then what I actually applied was, this was the error, and then I applied this, so overall, what was applied? A loop, which is one of the stabilizers. So I didn't do anything to the state. So the error plus the correction actually returned me back to the state. Good, so where is actually the problem? The problem comes from, if I have a larger torus, have this red thing. Let's go to the green thing. And suppose I have an error of x like this, acting on all these qubits. So it wraps around the torus. Do you see that it too also commutes with all the stabilizers? Because it also has intersection too with all stabilizers. With all stabilizers that touch it. So with every vertex, it has intersection too. So if I have XX, it will commute with this guy and this guy, it will commute with everything, but it is not part of the stabilizer. You cannot write this loop as a product of some subset of squares. Pick some subset of squares and then add x's on them. You cannot write it because it wraps around the torus. So this is a logical error. And it turns out that this is really the minimal logical error. You have to actually go topologically around the torus in order to create an error, which we cannot correct. So that's the distance of the code.
So how only handle X error? What about the Z error, Y error, so is error?
So, okay, I don't want to actually go into the Z errors. It's exactly the same thing. If you are familiar with, so this is an example of some huge area of homological codes from topology. And basically, if you're familiar with that, you can actually look at this is a path, you look at the copath, and so everything works in exactly the same way. But I don't want to look at this. For me, I just want the intuition coming from this. Okay, so I have this thing, this code, and it turns out that the distance of the code is really this. I haven't really gone into the details of the proof, as you've seen. It's just to give intuition. But the point is that this Dorit code can correct really square root of n over 2 errors. So it's a code that can correct many errors. And what I want you to take out of it is that this is a code, if you remember from my talk yesterday about error correcting code, what's the requirement from an error correcting code? If you can correct t errors, that means that any density matrix on 2t qubits will look the same for all states in the code, so that the environment doesn't learn anything from looking at those 2t qubits. So that means that for those states in the torus code, all states in this code will look the same if you look at about square root of n qubits. So the information is really globally distributed. Now, how many states, just for completeness, how many states are there? It turns out, this is why it's so beautiful, it turns out that the states correspond to the topological property of the torus. There is the sort of the basic state, and then there's a state that corresponds to applying a loop in that direction, applying a loop in that direction, and applying both loops. So this would be 0, 0, 0, 1, 1, 0, and 1, 1. So we have 2 qubits encoded in this code. Okay, so good. So this is a Dorit code. This is one way to see that it is globally entangled. Now I want to give another way to see why it's globally entangled, and that ties to David's talk from before.
So it seems someone here by taking n to be larger, you get a worse and worse code, not a better and better.
A worse and worse code in the sense of a rate, but a better code in terms of protection.
But if you have some probability for an error, then now suddenly the probability to be protected is like 1 over 10, so...
Yeah, I should say, so there's been a lot of analysis of this code. It's really it's a very interesting code. And if you analyze the random behavior of errors in this code, then things behave much better than just square root of n. It actually can correct the constant fraction of random errors. It has some threshold. And the probability that you sort of exceed that threshold grows decays if you take n to be larger. Yeah.
Real quickly, can you go over what the edges and vertices are again?
I don't understand the question.
Can you go over the picture again? Like, what are the edges and vertices in the grid?
The qubits are sitting on the edges, and the stabilizers are of two types. One is the vertex stabilizer, that for each vertex assigns an operator that acts on the qubits close to this vertex, and it looks like this. And the other type of stabilizers are those that touch the plaquettes, that surround the plaquettes and look like that, acting on the qubits on the edges of the plaquette, of the face. Okay? And you can check what they prove. So, okay, so now this is a Tori code. This is just so that you have an idea of the globalness of the entanglement. For me, you remember I had an EPR state as the first example of entanglement, and a one qubit entangled with a huge state in the circuit to atomic construction as the second example of entanglement. This is sort of a global entanglement where it's not a two-party entanglement, but it's sort of spread all over, all the qubits. Okay, so how do I capture in a different way the fact that it's globally entangled? I want to use the definition of constant depth quantum circuit and show that this guy cannot be, that any state in this code cannot be generated by a constant depth quantum circuit. Okay, so the claim is that if psi is in a Tori code, then no constant depth u, then there is no constant depth u such that u psi, u000 is psi. Okay, constant depth is just if you have a level of quantum gates, and the number of levels is constant. So this would be, for example, the unitary. These are states, these are qubits initialized at 0, and there are some constant number of levels of gates here. Okay, now such states that do have constant depth quantum circuits, let's call them trivial states. They're actually non-trivial because of what David showed earlier. They can generate highly complex correlations. But so why do we call them trivial? Essentially, it's the simplest state, except for just in terms of product state. But the reason we call them trivial is that if we have such a circuit, and we just want to compute a local observable of this circuit, that would be easy. Suppose I want to measure just this location. Then I could do that by just starting with all the qubits that are in what's called the light cone of this location, all the qubits that affect it. And the rest of the unitaries, the rest of the gates just will not affect that qubit. We actually didn't really sort of stress it, but it's a very important fact that if you have operations acting on different qubits, they commute. So this measurement commutes with this gate because it acts on a different qubit. So you can sort of delay all other operations to later, and that means that if you have a measurement acting on one location, or on two locations, some constant number, then the only computation that you actually need to do is this light cone computation. Okay, so now, why is this, why is there no constant depth u like that? So actually you have an exercise for that, but suppose, so I'll just do it very, very quickly, like a 2-minute sketch. Suppose suppose U000 is psi. What we're going to show is that psi is a unique ground state of local Hamiltonian. And why is that impossible?
Because it's entangled, so it cannot be.
Actually, Janice explained it yesterday in exercises.
I mean, not the stabilized units, but I understand. So isn't this psi somehow
Unique, importantly, unique. So the reason is that there are many other states, that there are 3 other states. It's not a unique ground state of the local Hamiltonian that describes it, because there are 3 more states that have the same, that will also be ground states. But there's a very simple argument. Well, because of the distance of the code, as we said, the reduced density matrix, in order for the code to be able to correct a large number of errors, the reduced density matrix to 2t qubits, if it corrects the errors, must be the same for all states in the code. Otherwise, somehow, if the environment addresses these t qubits, these 2t qubits, it will gain information, it will copy information. That's what I said yesterday. So the density matrices on a small number of qubits, a positive number of qubits, must be the same for all words in the code. So that means that their energy, any local Hamiltonian will not distinguish between different words in the code. You see, you're really not very happy about density matrices. Yeah?
The local Hamiltonian would need to have at least d over 2 locality or something.
I'm sorry?
When you say local Hamiltonian, you mean like 2 or 3, not like. So you would need
Not
to have.
like square root of n.
No, but
Constant.
square root. Okay, yes. So that's d over 2 big square.
Yes, exactly.
I have a question. So is this analogous to classical phenomenon that gives linear code of minimal distance and of d? You look at the less than d coordinates and how the distribution will be uniform. If you choose a random code word and you look at the less than the minimal distance of the dual code level.
But it's not true for the repetition code. It's not true. What do you mean a random code
So
word?
you see, no, take a code. Well, the dual code has minimal distance d. So if you give the metric that generates the code, then every d columns are really independent. So if you look at a random code word,
Yeah.
this code,
So I don't know if it's exactly the analog, but you can definitely use classical codes with this property to generate, for example, quantum Reed-Solomon codes exactly use this property. Okay, so psi is a unique ground state of a local Hamiltonian if this holds, and that's a contradiction because the reduced density matrices of other states are the same, so they would also be a ground state of the local Hamiltonian. So, okay, why is that true? Why if you have U like that psi is a unique ground state of the local Hamiltonian? Well, notice that if this is true, I'm using this equation. Suppose I'm looking at H, which is a sum of the projections 1, 1 on every qubit, I. What's the unique ground state of this Hamiltonian? Zeros. Thank you. Okay, the unique ground state is all zeros. So what is the unique ground state of UH U dagger? If this is the unique ground state of H, then I'm claiming that U, 0 to the n, is the unique ground state of this guy, rotated by, if I rotate H by this basis. But the thing is that if I rotate H, this is equal to a sum of the terms, 1, 1, where each term is rotated by U. And this thing, what is this thing? This thing is apply U, like in the circuit, apply this projection on 1 qubit, and then apply U dagger. And you can see that if you now apply U dagger, if you didn't have this thing, everything would have canceled. Each one of the gates would have canceled. You could have canceled U dagger, here you have U1, so here you have U1 dagger. They sort of appear in an opposite order. So if you didn't have this guy here, the projection, everything would have canceled. The only thing that prevents you from canceling is this light cone. So if you have a constant depth quantum circuit, everything cancels out, except for the effect of this guy on the light cone. So what's the size of the light cone?
Proportional to the gap.
Yeah, well, if it's a local circuit set on 2D, then it's proportional to the depth. If it's something that has no geometry, then it's at most 2 to the D or some constant to the D. Anyway, it's constant. So these guys will be constant. You have an exercise about that, so if that was too fast, you can go there, but we'll talk about it. But let's just take what I wanted to take from here. So commuting local Hamiltonians gives you states which are highly entangled. Their ground states can be highly entangled, and with very interesting properties. So let me summarize the questions before I move to PCP, where we will take this example and we'll understand more about it. So first of all, one question is, what's the complexity of CLH? Is it in NP or maybe QMA hard or somewhere in between? What's the complexity of generating states, ground states of CLHs like that? For the Tor code, we know it's polynomial, not trivial, not constant depth. But in general, we don't know. Complexity of ground state generation. In general, this question of complexity of ground state generation can be extended in various directions. So for example, it was shown that if the system is 1D, but the Hamiltonian is a spectral gap, it has a spectral gap which is a constant, then it was shown by Thomas and by Umesh and by that if the system is 1D and there is a spectral gap, then you can generate the ground states in polynomial time. In 2D we don't know, and it's a very big open question whether there exists efficient circuits in the case where the Hamiltonian has a spectral gap which is large, which for physicists is a very interesting property, which appears in many cases. So this whole thing leads to many questions that can be sort of, titled a complexity of ground state generation. Okay. Yeah, let's have a quick question before we move to PCP, in which we extend this. Yeah.
The light cone calculated from Lee Robinson?
I'm sorry? Yeah, the light cone is the computer science gentle version of the Lee Robinson map. Okay, good. So now, from this QMA theory, we want to move to the question of whether there exists an analog of the next step in NP theory. So the most important development in complexity over the past 20 years, maybe, I don't know, arguably, or one of the, at least one of the most important developments, is the PCP theorem. I'll tell you in a moment what that is, but essentially, we would like to know if a quantum PCP theorem exists, if it holds. There are various versions of that. Thomas will talk about one version, I will talk about another version, which is more related to this local Hamiltonian problem. And how many people have heard about the classical PCP theorem? Good, great. So you don't need me to advertise it. It's one of the most beautiful theorems that you can think about. Let me just say it nevertheless, for those who haven't heard it. So remember, sat is to decide whether whether a formula is satisfiable, or whether there exists one clause which must be valid. So in any assignment, there must be at least one clause which must be validated. The PCP theorem talks about a situation, a different problem, which seems to be much easier. You want to distinguish between the problem of satisfiability of a formula, in which you want to distinguish between either the formula is satisfiable, or at least 1% of the constraints must be validated. And you're promised that one of the two occur. Okay? Obviously, this problem is in NP, because it's easier. But notice that it's in NP with a weaker verifier, because the verifier, in order to know whether it is satisfiable or not, whether the formula is satisfiable, given a witness, all that the verifier needs to do is to sample the constraint. If the formula is not satisfiable, then at least 10% of the constraints, or 1% of the constraints, will be validated. So if you just sample the constraint, you will know. You will find it with some probability. You can repeat, and then you can amplify. Okay? So there is a very, let me write it. So SAT is decide between f is satisfiable or can satisfy at most m-1 constraints, where m is the number of constraints. Or validate at least one. And let's call it gap SAT, is the same, decide if f of formula is satisfiable, or say 1% of, let's call it m over 100 of constraints must be valid. Okay, and for gap SAT, there is what's called a PCP verifier, which, given a witness, just needs to randomly pick a constraint and check. And if the formula is not satisfiable, the problem will somehow spread all over the place. Okay, so it will detect it with some constant probability. So that's probabilistically checkable proofs. Okay. And the PCP remarkable theorem says that the class of problems that can be checked by this probabilistically checkable checking verifier that just looks at the witness, at the proof, and randomly picks a constraint, that class, which we call PCP, is equal to NP. Seems to be a much weaker class. A different way to say it is that gap SAT is NP hard. And yet, a different way to say it is, I'm sure you've heard of it, but for those of you who haven't, if you have a crypto paper, papers are hard to check, the errors, and you need to review it, okay? Now, okay, sometimes the errors are just spread all over the place, so you can easily detect that it's wrong. but suppose it's not spread all over the place, and you really want to find the mistake, you're sure that there is a mistake, you really want to find it, you will have to read the entire paper, which could be very long. So the PCP theorem tells you that there is a way to take the paper, for someone who wrote the paper, to put it in a different format, which is not much longer, such that we will only need to randomly pick the constant number of locations, perform a very simple test, and decide whether the paper is wrong or not. There is, of course, a downside, which you will not understand anything about the paper, but that's the difference between verification and understanding. Okay, so papers. That's a different way of explaining the PCP theorem. So that's a very deep theorem. Let me prove it. No, I was just checking too much. Okay, so the proof of the PCP theorem.
I'll prove it tomorrow morning.
Okay, the proof could take a course. It's a very complicated proof. It's a very, very beautiful proof. If you've heard about the PCP theorem, I'm sure you've heard of how beautiful the proof is. Essentially, the idea of the proof is something like you want to start with the situation in which either 1/n of the constraints are violated or 0 must be violated. That's where you start with. That's sort of the SAT case, where this is now a fraction of the constraints. And you want to amplify it so that this is epsilon fraction, and this is still 0. You want to somehow map the initial formula to a new formula, such that if the original formula was satisfiable, then so is the new one. But if the original formula had just one constraint that had to be violated, then the new one, epsilon n constraints, will have to be violated. And the way this is done is basically you make, essentially, don't catch me in the word, essentially you make the constraints larger, and therefore you somehow make the errors spread. But now the constraints are much less local. You manage by this to somehow increase this a little bit, your sensitivity to the error. But then you have to make the constraints local. You pay a little bit for this, but you make sure that this payment is not too big, and you do that by error correcting codes. This is a very clever thing for physicists. This is a sort of, you do this repeated in an iterative way, logarithmically many times, until you get to epsilon. For physicists, you can maybe think about it as some kind of a renormalization group, where every time you flow from here to here. Every time you sort of get closer. Forget about this if you don't know what I'm talking about. Okay, so now, this had amazing applications to crypto, to complexity, to proving that problems are hard to approximate, of course, to coding theory. It raises many, many questions in error correcting codes. Okay, so now we want the same in the quantum world. It was so good, we also want to understand what's going on. Is there a quantum analog of the PCP theorem? I'll talk a little bit later, about other motivations, except for just you want to mimic the classical case. Already the motivation of mimicking the classical case is very strong, because even mimicking the QMA hardness result, the Cook-Levin to the QMA hardness result led to really very deep implications. So even just trying to do that will teach us a lot, but I'll tell you more about the motivation, other motivations later. Okay, but what would be a quantum PCP theorem or conjecture? As I said, there are various variants. Well, let's write one variant, QPCP conjecture. Before that, let me write gap Hamiltonian. So gapped local Hamiltonian is the same as the local Hamiltonian problem, gapped local Hamiltonian problem, except now the ground energy is either less than A or larger than B, but A minus B is a fraction times the constraint. So you can actually take A to be 0, and then B will be some constant times the number of constraints. So you're given H, local Hamiltonian, and decide whether the ground energy is 0 or larger than epsilon m. Yeah.
So you said that you could assume that, but you also said that in another version maybe where A is some other small quantity. So are they equivalent? So if somehow,
What is A?
so they're A and B, right? And then now A and B are far apart, so that's linear and fraction in M, like that. So but here also making sure you're still in A to be 0. So is it the same problem? Is it an easier problem?
I don't know if it's precisely the same, but I think they can be related.
It's not a good question. There's a class 3 main 1, that's the one side of the
Yeah.
and it's related.
But I think it's the only thing that matters. Yeah. So there's something else to check other than the difference between the completeness being 1 or not, I think, but we can discuss it later. Okay? So this is the gap local Hamiltonian problem, and the QPCP conjecture says gapped local Hamiltonian is QMA hard. Okay, so now you can also have another version of QPCP conjecture in which your verifier checks only 3 or 4 qubits of the proof randomly, and then applies some quantum computation after reading those qubits or doing something with those qubits. That's sort of a PCP version, probabilistically checking verifier version of this. I won't write it because I don't want to get into it. In fact, they're equivalent, and just for the experts, they're equivalent under quantum reductions, quantum polynomial time reductions, and they're not known to be equivalent by classical polynomial reductions. Okay, so this is our question. Now, what makes this question so difficult? So this is a major open question. We don't know the answer. And actually, we don't have a guess, I think. I don't know. It's not that the community agrees that one thing is correct and should be proven. What makes this very difficult is that this steps in the proof that I sort of described, of making the constraints global and then somehow reducing their locality in some way using error correcting codes, not quantum. These are local things. Now, if you recall, in the proof of the quantum Klotz-Levin theorem, that was exactly the problem. Remember, there was this issue of checking locally that 2 states are the same. We couldn't do that, so somehow we needed to give up our notion of locality and in some way, and talk about checking locally whether these 2 states are the same by entangling the global state to another qubit and performing the test on that qubit. So we don't know how to do that. We don't know. It seems that all the steps in the proof are very local, and we don't have this trick in the quantum PCP situation. So there are several papers that discuss the difficulty, and I won't get more into the difficulty because I want to tell you. You can read the paper. There's a survey of Thomas and myself and Tyrod about it, where the difficulties are sort of discussed, some of the difficulties. I think it will be not so interesting to tell you about what we really don't understand. So let me tell you something that we do understand a little better, I think. And this is another conjecture that's called the NLTS conjecture, which is employed by the QPCP conjecture. Okay, and it seems to be much easier. So let me tell you about that conjecture. I need another word. Okay, I'll just draw this later again. So there is this 1 over m0 going to 0 and epsilon. And by the way, if this QPCP conjecture holds, what that means is that local Hamiltonian is QMA hard. That actually means that there is this mapping from a local Hamiltonian to a local Hamiltonian with this gap also in the quantum world. And note that again, this mapping, just again, I'm saying for the experts, could be quantum polynomial type. Okay, so the NLTS conjecture. What's the NLTS? Too many letters here. NLTS is no low energy trivial states conjecture. Okay, so no low energy trivial states conjecture. And what the conjecture says is that there must exist a family of Hamiltonians such that all their low energy states, where low energy is the energy below epsilon times m, are non-trivial in the sense that I said before, meaning that they cannot be generated by constant depth quantum circuits. So let me write it. There exists a family of Hamiltonians, and then going to infinity, and m constraints. And there exists an epsilon larger than 0, such that all psi's with psi hn psi less than epsilon m are non-trivial. Meaning that they require more than constant depth quantum circuits to generate. So why is this NLTS conjecture following from quantum PCP? It's not directly follows, you have to assume something. Okay, so suppose not. Suppose all Hamiltonians have somewhere in their energy spectrum below epsilon m. So this is the spectrum of the Hamiltonian. That's all the eigenvalues, and this is m. Number of constraints. Constraints are projections, so energy cannot be larger than m. Somewhere this is sort of low energy. Low is not exactly low. It's less than a constant fraction. Suppose for every Hamiltonian, there is a state with energy less than epsilon m, which has a constant depth quantum circuit. Then I'm claiming that if I have a gapped local Hamiltonian, and all I have to decide, if I'm given an instance for this gap local Hamiltonian problem, and all I have to decide, I'm given a Hamiltonian, and I need to decide if its energy is 0 or it's above epsilon m. So it's one of these cases. So I'm claiming that the witness, if this is the case, the prover could give me, instead ground state, which could be highly entangled, the proofer could give me this constant depth quantum circuit, but as a classical description, and then I could have computed the energy from this constant depth quantum circuit, because the energy is just a sum of local terms that I can compute the observables of, right? That's what I said before, that if you have an observable, I can compute it if it's local. It's a local Hamiltonian. So I can compute the energy given a constant depth quantum circuit, and I will be convinced that the energy of the given state is here. Since I'm promised that either the lowest energy is here or here, that would be a proof that I'm in this case. Okay? So if this is QMA hard, if this problem is QMA hard, what I've shown is that there will be witnesses here which are classical, and that would show that QMA equals QCMA. QCMA is this problem with classical witnesses. So assuming QCMA is not equal to QMA, so assuming that not all ground states can be generated efficiently, which is this assumption that we have been talking about, under this assumption, the QPCP conjecture implies the LTS conjecture. Okay?
So how does this relate to this code? So
Exactly, that's my next step. So now let's go back to the Torah code and see why it doesn't. So let's see, maybe it's an LTS example. Okay? So I don't know what to erase here. Okay, I think the local Hamiltonian problem by now you should know. So, and maybe I'll put this Z here so that I can erase. Okay, so so now you can ask, aren't these stabilizer codes like the Torah code, or are the Torah code states an example from the NLTS for states, since that all their low energy states are difficult to generate or highly entangled? So we've shown already in the beginning of my talk that the ground state is indeed non-trivial. It is highly entangled, right? I've shown to you that this state, that any ground state or any state in the Torah code cannot be generated by a constant depth quantum circuit. So what else do I have to show?
what was the state, this green state over there? What is this error, this was outside your...
Yeah, that's not, I don't know. Yeah, is it a state with small energy?
Right.
Actually, the state with the green is a state with zero energy, right? Because it's a logical error, so it's in the code. But you're right. Let's just talk about some error that is not wrapping around the board, but just half of it, say. So that state is not in the code. What's the energy of that state? Exactly. So what is it? It's very small, right? So this state is a low energy state, and it looks like it will be still hard to generate. So that's not okay. That's sort of a positive evidence. So I want to claim that the Torah code is not an NLTS. So what I want to show is that there are low energy states which can easily be generated, meaning can be generated by a constant depth quantum circuit. And this is how I'll do it. I'll take this torus, think about it as a grid, and let me copy it here so that I can draw on it. Okay, make it smaller. And now I'm going to cut it to constant size squares. Okay, so suppose I'm talking here about epsilon m. I'm going to take delta, which is, I don't know, much smaller than epsilon, and I'm going to look here at squares of size 1 over delta. It's a constant. And here also 1 over delta, and I'll cut the torus to squares of size 1 over delta. Maybe I'll use a different color. And what do I mean by I cut the torus? Everything that touches these lines, I remove. Constraints that touch these lines, I remove. But the rest I leave in place. So how many constraints did I remove? If this is square root of n, and this is square root of n, how many constraints did I remove? Well, I removed, so how many lines, how many columns are there like that? They're square root of n divided by 1 over delta, so it's delta square root of n. And each line gives me roughly square root of n constraints. And the same, this is for the columns, the same for the rows. So it's something like 2 delta n constraints. So it's some fraction of the constraints, but the fraction is much smaller because I chose delta to be small, much smaller than epsilon. So the energy okay, so I want to create a ground state which satisfies all constraints except for those constraints. And I want to do it easily. How do I do it? Any idea? There is no constraints here. Now, it looks like this. Huh? Yeah, I just create the ground state of each part separately. So this is a constant size. It's just easy to generate the ground states of constant size. I take the tensor product of all of them, and I get a state which is constant size, constant depth generated. I generate this and this and this sort of in parallel. And the energy is at most 2 delta n. So it's a low energy state. So notice that the thing that I've used here is the fact that I could cut the torus to small parts by removing a small number of edges. So any code that will sit on some graph of this property will have this problem. Okay, so if you're familiar with the notion of expanders, you have to somehow put your graph on a highly connected, put your code on a highly connected graph so that this phenomena doesn't happen. Okay, so that's the NLTS conjecture, and this is we don't know, even though the words Probus sort of proved something which seemed to be very close, but it's very different than this, and right now it's wide open. We don't know if this is true or not. Yeah.
I have a question, so maybe it's unrelated. So for this Dorit code, you had this local constraint, and the minimal distance was about root n. So the fact that the minimal distance is root n and not n, does it have any relation to this conjecture, or so unrelated somehow?
I don't know actually. It's a good question. Maybe I'll say something in a moment. No, I won't. But we can talk about it later. Yeah.
So you mentioned that obviously the QPCP, if it is true, could lead to the NLTS conjecture. But I'm wondering if you can go the other way around, because if you get a choice of 2 delta n and you can set your deltas clearly, you might be able to find an epsilon above which it is easy to show that you can solve the gap.
Yeah, so you somehow, this seems to be much more difficult because you need the mapping. You need to actually know how to map states. So the reason why these NLTS Hamiltonians would exist is that somehow these would be the output of this mapping. But how exactly this mapping will happen, that is a different question. So I want to mention, first of all, this is, I think, a very interesting question. it probably needs something, I don't know, from which, so one possible direction would be to look at high-dimensional expanders, and there are other possible directions. Yeah.
Are you defining this only for stabilizer-like codes? Or
No.
Because you're talking about
No.
this one. This is just for more general.
Right.
But second, I think was this, if I take a 4-dimensional Dorit code, we do know that all its like the below some temperature, which means below some finite energy density, all states are highly entangled.
4 dimension, same argument. 4 dimension, you cut. It's the same argument exactly. Everything in a Euclidean constant dimension, you can cut it to small squares by removing a small fraction of the edges. So, okay. So now let me just mention one problem that's related to it, and that's the maybe more for the experts, and then I want to talk a few minutes about the motivation, physical motivation. So the problem that I want to connect it to is local testability. So the notion of locally testable codes. So let's actually go in the wrong direction and define it from the quantum side first, instead of first defining the classical and then quantifying it. So here's the star code, and suppose I have an error which is rather long, it's square root of n, and now count how many violations are there. How many, we already counted it, so we have some string like that. It's square root of n long. How many violations are there? How many stabilizers are violated? 2. It's just the endpoints of the string. A quantum locally testable code would be a code in which if the error is large, meaning if the distance from the code is large, then the energy, meaning the number of violations, will be large. Classically, this is the same thing. There's a code where if your string is far from the code, then there are many violations, many parity checks that are violated. And this is related to PCP because sort of the number of violations is what's important for you in order to detect whether you're far or close to the code. If there are many, you can randomly pick them. And indeed, locally testable codes appear, they're central to the PCP proof and to various constructions of it. And it's a big question whether quantum locally testable codes exist. There are various limitations that we know, which I won't get into, but one thing that I did want to mention is a very beautiful proof by Dorit Aharonov that shows that quantum locally testable codes, if they exist, and if they have constant distance, fractional constant distance, that is distance which is a fraction of n, then they imply the NLTS conjecture. Okay, so from QLTC, you get NLTS. If those codes are stabilizer codes, in fact, the restricted version of them, and their distance is large. So there should be some connection, and this is an open question to really understand these connections. Okay, let me end with what I wanted to say about the motivation, but are there questions about this before I continue to there? Yeah.
Did you do anything with the other way around?
No, I don't know. It's okay. We know quite little about this. By the way, also classically, we don't know that PCP implies NTC or NTC implies PCP, even though there are strong connections between them, but there's no formal proof that one implies the other. Okay, so So if there are no questions about this, I just want to yeah.
Are there QMA hard problems that have fast quantum approximation algorithms?
Fast quantum approximation algorithms for, so approximating, you mean for
Like in classical theory, right? NP hard problems.
I'm blanking out, need help. But nothing like knapsack or anything.
With like boson sampling, I think? That you can approximate boson sampling with a quantum system, but
But boson sampling is not QMA hard. It's QMA hard because it's Sharpie hard, so I don't think there's an interesting answer to your question, but
I mean, if you
but
prove
in
that
the sense that Sharpie problems can be approximated in P, then yes, because QMA is in Sharpie. So yes, but it's not an interesting answer. You're actually looking for a quantum problem, so I don't know. Okay, so I want to just connect this to I'm wondering whether I should do it. Okay, let me just give it the intuition. I want to connect this to the question of fault tolerance and the question of robustness of entanglement. So really, when we talked about fault tolerance, David also mentioned fault tolerance, and fault tolerance should be thought of as answering the question of whether global quantum states, meaning global entanglement, can be maintained at room temperature, meaning in our world, when there's noise, and the threshold theorem, which we didn't actually state, says that if the rate of the errors is less than some constant, which corresponds to the temperature in the system being some constant, then we can correct. And this is sort of a dynamic version of, yes, we can maintain entanglement, global entanglement is robust. Okay? Quantum PCP is in some sense the static version of that. I want to claim that quantum PCP says quantum entanglement, global entanglement is robust in the static state of the system. So what is the static state of the system? We talked, 2 days ago about the fact that when you have a physical system, you wait long enough, it could be exponentially long, the system decays to its ground state. And I said, when it decays to its ground state, the temperature is very low. Let me just state it more in a less physicsy way, but borrowing this from physics. So physics tells us that at room temperature, whatever that means, we have some intuition of what temperature means. Room temperature means constant temperature. The system equilibrates, meaning its limiting distribution after we wait a long time, is called the Gibbs distribution. The Gibbs distribution is this distribution that says that if the state has energy something, its probability behaves like this. So probability of a configuration sigma, or of a state, if it's a quantum system, would be e to the minus 1 over the temperature times the energy of this sigma. Okay? And in fact, you can write it as equal, and here you have the normalization factor, which is called the partition function. Okay? So if t is 0, it turns out that this limit is just, you are in the ground state. But if t is larger than 0, then there is some, it's called the Gibbs distribution, Gibbs Boltzmann distribution, there is some decay. And you have some chance of being not in the ground state, but as the energy grows up, you have a smaller and smaller chance to be in the ground state, to be in that state. Okay? Now, I want to say that roughly the meaning of the quantum PCP theorem is that it is QMA hard for the system to relax, or there are systems, I said the QPCP theorem, it's QPCP conjecture. If it's correct, it would imply that there are systems for which it is QMA hard for the system to relax to its Gibbs distribution. Or in a different way, it says QMA hard to sample from the Gibbs distribution of that system. Why is that? Well, again, it's the same argument as we had here. Essentially, I want to say that if I relax to the Gibbs distribution, suppose, remember, I need to distinguish between the spectrum being here, this is the ground state, and this is various excited states, and this is the energy. I need to distinguish between this case and this case, where this is epsilon n. And it's an easy calculation, which I don't want to do now, but it's a very easy calculation. The idea is that at room temperature, there is a constant temperature, such that if we relax the system to its Gibbs distribution, then, and we sample from it, if we relax this system to its Gibbs distribution, meaning it's now distributed according to this, and we take the entire probability to be above epsilon m, then that probability will be very small compared to the probability to be here. And the reason essentially is that, well, the energy is very large. It's a fraction of m. So the probability with respect to this guy decays like e to the minus epsilon n. Now, there could be many states, but since m is at least n, then even if you take that probability, e to the minus epsilon m divided by t, and you give it factor 2 to the end in front of it, still it will be much smaller than the probability to be here. So if you just let the system relax to its grounds, to its Gibbs state, and you sample, you will, with good probability, measure something here, and therefore you will answer a QMA hard problem. Because if you sample something here, you will be able to distinguish between this case and this case. Okay? So repeating the argument, if the system can relax efficiently to its Gibbs distribution, if the system can relax to its Gibbs distribution, then it solves a QMA hard problem. Because I let it relax to its Gibbs distribution, I sample, and if we're in this case, I will with good probability sample here, and I will know that I'm not in this case. Okay? So why is that interesting? This means that even at room temperature, typical states are highly entangled because we're talking about QMA hard problems, and therefore the states cannot have efficient descriptions. Okay? So I think this question is very interesting, both because of this, but mainly because it definitely probes our very intuition about this notion of global versus local entanglement and everything related to it. Any progress in that will have to somehow tell us something about global entanglement. Questions about it? Yeah.
So we relaxing system, is it an open quantum system or closed?
In this relaxation,
yeah.
Well, the system cannot relax to a Gibbs distribution without being open.
Or you could say relax system one minor element and
yeah, but then someone has to apply these operations. So, yeah, it's an open quantum system. I think this set of questions here is really, there's lots going on here, and it touches many, many different questions. Also about lower bounds of quantum circuits from the point of view of computer scientists. Okay, shall we have a break before or exercises? Now exercises. There's a small break before exercises, or? Okay, free choice.